Hello everyone, thank you for watching my video today. And in this video, we're going to talk about a few different things. One, we're going to start talking about working with geometric series. This is a lot, really, a pre-calculus review. But also then we're going to start talking about the nth term test for divergence, which is not a pre-calculus review. All right, so let's start with talking about geometric series. So first of all, what is a geometric series? That is just going to be where every successive term is multiplied by the same number. So you can see here's an example of a geometric series where every successive term is multiplied by 2. The general form of an arithmetic series is a sub 1 times r to the n minus 1, okay? And we're going to start talking about converging versus diverging a lot more here. An infinite geometric series converges to some number if r, its absolute value, is less than 1. And that number would be a over 1 minus r. All right, so to sum that up, if you have a geometric series that's infinite and the absolute value of r is less than 1, you would use the formula a over 1 minus r to find the answer to that summation. A couple quick notes over here on the side. A geometric series does not have to begin with index n equals 0 like I have here. It could be anything, okay? A more intuitive way to compute the sum is to think of the sum as first term divided by 1 minus common ratio. Instead of actually trying to memorize the formula, just think of first term over 1 minus common ratio, okay? So example 1, basic straight here. Let's just figure out, is this geometric or not? If it is, what would r be? Okay, so this one is geometric. Think of it as like there's like a 1 here, right? So this is geometric. And r would be 1/2. Which means if this was infinite, which it isn't, but if it was infinite, we would be able to find its sum. Second one. Okay, so 1 over n. This one is not geometric. You're not multiplying by the same number each time. And if you don't know that, you could just put the first couple numbers in. You would get 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5. We're clearly not multiplying by the same number each time. Third one, this is obviously not geometric. This is linear, so this is actually called arithmetic. So this again would be not geometric. All right, so now let's get into the calculus, which really, again, is kind of a little bit of pre-calc as well. Convergent versus divergent geometric series. Evaluate each of the following geometric series or state that it diverges. You can see that all of them go to infinity. So these are called infinite geometric series. Our goal is to figure out what r is. If r is bigger than 1, it diverges. If r is less than 1, we can find the sum. Okay, so the first one, r is 1.1, which is bigger than 1. So this one diverges. And by diverges, we just mean that the answer goes to infinity. B, maybe a good way to think of this would be 1 over e to the n or 1 over e to the n. So we're multiplying by 1 over e every time. Okay, so this is geometric, obviously. And 1 over e is less than 1. I don't know exactly what it is, but I know that's less than 1. So we can find the sum of this series. So the sum of the infinite terms would be the first term, which, let's see what it would be. If we put 0 in here, e to the 0 would be 1 over 1 minus r. Okay, so that would be 1 over e minus 1 over e, which is e over e minus 1. Okay, and that's good enough for our answer. Now, if we had a calculator, we could type it in our calculator. Let's see what we get here, 1.582. Okay, but either of these would be an acceptable answer. C, r here is obviously negative 0.75, whose absolute value is less than 1. So we can find the sum. So the sum's going to be the first term. The first term, if you put 0 in here, we get 3 times 1, which is 3. So 3 over 1 minus r here is negative 0.75. So it's 3 over 1.75, which you can think of as 3 over 7/4. Do that right? I think I did that right. So it'd be 12/7. And again, if we had a calculator to do that, let's see, type that in my calculator here. 1.714. This one, it might not look geometric at first, but we can rewrite this as, well, not the whole thing. We can rewrite the nth term as 3 times 1/2 to the n, or 3 times 1/2 to the n. So now r is clearly 1/2. So this does converge. S of infinite terms is going to be 1/1 minus 1/2. Oh, it's not 1. Sorry, the first term's not 1. It'd be 3/1, which is 3. So 3/1 minus 1/2, or 3/1/2, or 6. E, r here is 3/2, which is clearly bigger than 1, so this diverges. And F, e over pi to the n. E over pi, if you don't know what that is, it's about 2.7 over 3.1, which is definitely less than 1. So this one does converge. First term would be e over pi to the 0, so 1 over 1 minus e over pi. All right, so that would be 1 over pi minus e over pi, which is pi over pi minus e. And if you type that into your calculator, (7.421). So either of those would be correct. Example 3, write 1.025 repeating as a geometric series and express its value as a fraction. All right, so 1.025 repeating, that's the same thing as writing 1.025, 25, 25, 25, so forth and so on, right? So we can think of that as 1 plus 0.025 plus 0.00025 plus 0.0000025, or in fraction form, 1 plus 25 1,000ths plus 25 over 100,000s plus 25 over 10 million, so forth and so on. Right? Which we can continue to write this down a little bit more as 1 plus sigma of, I'm going to go 2.5 times 1 over 100 to the end. There's a couple different ways to write this. This is just one way you could do it, where n equals 1 to infinity. All right, so the index doesn't have to start at 1. You could start a couple different ways. You could have done this as 25 and changed this to something else. There's a lot of different ways to write this signal notation. This is one way that I came up with to do it. So if we're going to find the sum of that summation there, if we put 1 in, we get 2.5 times 1/100th, which would be 0.025 over 1 minus 99/100th, so 0.99. And if we put this, we can just put this into our calculator. Oops, I meant to say this is 1/100th, so 0.01, which will end up being 0.99 here. And convert to a fraction. All Right, and then we're gonna, don't forget to add the 1 out in front here. So my final answer would be 203 over 198. Or you can put it in decimal form as well. It's fine. All right, so that's it for topic 10.2. Now we're going to start looking at our tests for convergence or divergence here. So the first test we're going to look at here is called the nth term test for divergence. Okay, so first of all, the limit of the nth term. If this converges, then the limit must be 0. Before we go down here, let's go to the side over here. Very important note here. Just because if this is true, does not mean the other way around is also true. If this is true, we don't know if this converges or not. We say the test is inconclusive. Okay? Okay, it seems rather intuitive that a series cannot possibly add to a finite sum unless the terms themselves approach 0. What is important from the above theorem is that its contrapositive is also true. What that means is if this is not true, then this is not true. So if the limit does not approach 0, then this diverges. Okay, another quick note on the side over there. We're going to start to see a lot more factorials soon. As you can see, they don't work well with all of our calculus that we know. So what we just want to do is we want to think, how do they impact the series that we're looking at here? And that's really the best way we can think about it. We just got to really think our way through anytime we see a factorial. Okay? So let's take a look at the nth term test. A couple problems here. Determine if the following series converge or diverge. Okay, so the first one here, we're going to use the nth term test. So the limit as that approaches infinity of the nth term. Now, if you plug infinity in there, you can get infinity over infinity. So using L'Hopital's, we get 1 over 1, which is 1, which is not 0, which means that this one definitely diverges. Second one, so limit as n approaches infinity of 1 plus 3 to the n over 2 to the n. If you put infinity in there, you get infinity over infinity again, which doesn't really help there. So if you use L'Hopital's, you would get 3 to the n times ln 3 over 2 to the n times ln 2. All right, the ln 3 and the ln 2 don't really matter. We're talking about infinites here. So we're left with this, which is basically 3 halves to the infinity. Since the 3 is bigger than the 2, that's going to go to infinity. So therefore, we can say this also diverges because our answer was not 0. Question C. Limit as n approaches infinity of 1 over n, which is be 1 over infinity, which is 0. Aha. All right, so remember, we cannot say that this definitely converges, but what we can say is the test is inconclusive. All right, we can't say that it diverges. We can't say that it converges because we're not sure, so we just say it's inconclusive. And here's a factorial one that we were talking about earlier, right? So n cubed over n factorial. So we want the limit as n approaches infinity of n cubed over n factorial. So again, I just said earlier, just start think of the logical impact they have on this series, okay? How do I do that in this one? Which of these is going to get larger faster? All right, think about 2 cubed versus 2 factorial. Well, 2 cubed is bigger. How about 3 cubed versus 3 factorial? 4 cubed versus 4 factorial. At some point, the factorial is going to start getting larger a lot quicker. Let's do it. Let's think of a quick example here. Let's see. I'm just going to throw a number out there. How about let's see what 10 factorial is. Okay, so 10 factorial, for example, is 3,628,880. But 10 cubed is 1,000. And you can see just how much bigger the denominator has already gotten over the numerator. And think about, as we go to infinity, how much bigger it's going to get. So this is going to grow a lot faster than this will grow, which means this is going to go to 0. Because it's going to go to something over infinity, which will go to 0. So since that is 0, again, we would say our test is inconclusive. We can't say that it diverges for sure, but we also cannot say that it converges. Okay? So that'll do it for our lesson today on topics 10.2 and 10.3. I hope you enjoyed our video, and we will see you again next time.